The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining us on our call today. My name is Mike Crittenden from Transcat, and I'll be your moderator this afternoon. Our webinar topic is motor analysis with a power quality analyzer. This topic is being presented by Jason Honeycutt from Megger. Jason is an up-through-the-ranks guy who started with Megger in 2008 in the test and calibration department for high-voltage products. He was promoted in 2016 to Power Quality Applications Engineer for the U.S. distribution team, where he conducts demonstrations for customers and training sessions for distributors, sales staff, and end users on power quality. We expect today's presentation to last roughly 30 minutes, and then we'll answer any questions that have been submitted. At any time during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Jason.
Hello, everybody. Thank you for joining us today. Again, my name is Jason Honeycutt, and today we will be doing a presentation on motor analysis with a power quality analyzer. We will talk about different motor problems and how power quality affects them. Motors need to be maintained on a regular basis because they are up and running all the time. So one small problem can cause an organization a great deal. They should be inspected regularly, and other maintenance activities should be performed to ensure efficient operation. And whenever a problem happens, it should be corrected immediately to avoid any more loss. So to avoid downtime, costly rewinds, and replacements, we want to use good equipment, test regularly, and trend the data. Let's talk about some of the motor failures. We have bearings, which are the majority of the motor failures, followed by windings, rotors, and others, which are usually manufacturing defects and things of that sort. So this slide, it depends on your configuration of your motor in your system. This slide is going to show you how to hook your power quality analyzer up. If you have a Delta 2-watt configuration or Y 3-watt configuration. If you have a Delta, we're going to hook up phase A and B current to one leg, phase A current and voltage to this leg, and the return or neutral to this leg. The phase C in the unit will not be used. A good power quality software will make those calculations in the software. And this is the vector diagram that you would see. In a Y configuration, we're going to connect phase A voltage and current to this leg, phase B current and voltage to this leg, and phase C voltage and current to this leg. And then our return or neutral will be onto this leg. And we will see this vector diagram on our unit. The PQ unit is going to help you determine the quality of the power driving your motor, and it's also going to let you know if there are harmonics, transients, or other PQ events that may be affecting the life of your motor. So let's talk about winding failures. We can see in the top right picture there's some burnt shorted coils, which could have been due to a transient, which is a high magnitude, high speed voltage spike. They are usually caused by lightning, and this is what a good power quality analyzer's software will be able to show you in the chart of catching a fast transient. So good power quality analyzer is going to capture these transients down to 1 microsecond. Heating effects will decrease the life of your motor. It'll reduce the viscosity of the bearing grease and then cause the windings to burn up, as we see in this picture here. So some of the causes for motors heating would be under voltage. We can see we have 100% of voltage here, and then our voltage gets lower here. Since motors are constant power devices, as the voltage goes down, the current must go up, and so does the heat. Some of the causes of under voltage would be things like cat bank switching off, switching on big loads, or overloaded circuits. Here we have the opposite situation. It's at over voltage. So we can clearly see our voltage tops out over the 100% line there. And an over voltage can drive up the amperage and the temperature even on lightly loaded motors. As well as the inrush current goes up with higher voltage, especially with heavily loaded motors. Some of the reasons a overvoltage may happen would be things like a large load, such as the motor shutting off, cat bank switching, or even wrong tap settings on the transformer. Overloading. Here we have our donkey who's overloaded. He can't move anywhere. He's basically stuck. But in the case of an overloaded motor, individual motor components, including the bearings, windings, may be working fine, but the motor is going to continue to run hot. The primary symptoms to look for here would be excessive current draw, insufficient torque, and even overheating itself. Unbalance is another cause of motors to heat. We can see this phase B voltage is slightly lower than phase A and C voltage. And that correlates down here into the current. So just 1% of unbalance in the phase voltages can cause 6 to 10% unbalance in the phase current. This can lead to greater heating effects and individual coils burning up and insulation melting, leading to shorted coils. Harmonics also create heat, and harmonic is a multiple of the fundamental frequency. So here in America, that's 60 hertz. So what we're looking at here is a bar chart, harmonic bar chart of what a good power quality analyzer software should be able to give you. This first line is our fundamental frequency, so it's going to be 100%. That's our 60 hertz. So our second order is going to be 120 hertz. Our third order, 180, and so forth. The higher the order harmonic, the higher or the more heat it creates. Now the thing about harmonics is they create what they call eddy currents in the wires. And these eddy currents create magnetic fields that push the current going through those wires to the outer edge of the wire, which is known as the skin effect. This increases the heating effects in the wire. But in addition, especially in motors, when you have adjacent coils or adjacent wires named a coil, this magnetic field will be pushed to the adjacent wire and then to the outer edge of that wire and then the outer edge of the next wire. And that's called the proximity effect, and it just further increases the motor heating effects. So VFDs, or variable frequency drives, use high-speed switching IGBTs, or insulated gate bipolar transistors, and they create a great deal of high-frequency voltage harmonics, like we can see here. We can put a filter on it and create a relatively clean drive current, as we see in this picture. But high-frequency harmonics still exist. Sorry about that. And we can see again our bar chart. And the higher the order of the harmonic, the hotter it's going to get. You're probably aware of this, but bearing failures are due to things like poor lubrication, misalignment, faulty mounting, contamination, and poor sealing, but also due to electric current passing through the bearing and vibration. So when current passes through the bearing, it creates arcing. And this arcing creates pitting or fluting in the raceway. So one of the things to do when troubleshooting a motor is to look for pitting or fluting, as seen here in this picture. Pitting would be more like little dings, and this is fluting. There shouldn't be any voltage on the shaft, but if there is, the discharge between that bearing and the race causes this pitting and this fluting effect. Mechanical imbalance, faulty bearings, and misalignment are causes of vibration, but so are negative sequence harmonics. What we're looking at here is a detailed harmonic analysis of what a good power quality analyzer would give you. You got your bar chart again here. We can see our total harmonic distortion and the odd contribution and even contribution of that harmonic distortion, as well as cycle through our waveform. If we look over here, we have a dominant fifth and seventh harmonic, which are commonly caused by 6-pulse converters, and they produce this dominant fifth negative sequence harmonic. They are present in 3-phase power supplies that are often used in VFDs, but these negative sequence harmonics have magnetic fields that rotate in the opposite direction of the rotor's magnetic field, which create counter-rotational currents and lead to vibration. A good power quality analyzer is going to record both voltage and current harmonics as well as interharmonics. So as we can see here, a rotor bar can be completely or partially cracked. And these can be due to things like manufacturing defects, of course, frequent starts at the rated voltage, thermal stresses, and of course, vibration. What we're looking at here is sidebands or interharmonics. So there are fundamental frequencies here in the middle. Interharmonics are the frequencies to the immediate left and right sides of the fundamental frequency. And they are usually the cause to rotor bar damage when it's due to harmonics. So again, a good power quality analyzer is going to perform an FFT or fast Fourier transform analysis to view the current harmonics and identify these high sideband frequencies. So a couple important things to remember when motor testing. Power factor, of course, for those unfamiliar, 0 to 1 is the number for power factor, 1 being the best. And it's more or less making sure the efficiency of your power. Are you getting the best for your money and the power out of your facility? 1 being the best. So this example here is a screenshot of an online waveform analysis of a good power quality analyzer looking at power factor. And so we have our 1 here, and we see a couple spikes down. Even this long one down, still only down to 0.97. So this is a good example of a good power factor. What we're looking at here is the total demand report that a good power quality analyzer software can give you. You will see the KW, KVAR, KVA, and then again, of course, the total power factor. This example here was on average, as you can see, about 0.6, which is not good. Anything under, anything above 0.9 is good. Anything, under 0.8, you're getting pretty hairy. So this particular facility was running several hundred motors, and it was bringing down their power factor. And a low power factor can cause your motors to be unable to obtain full power. So again, a good power quality analyzer is going to record all these parameters, including power factor. Motor startup. You're going to want a good analyzer that can record all parameters on a cycle-by-cycle basis. So when the motor starts up, you can capture over 600 channels, or excuse me, 600 cycles of inrush current. We have our cycle-by-cycle voltage and current waveform chart and our inrush current waveform chart. Another thing a good power quality analyzer is going to allow you to do is hook up remotely. This is ideal for long evaluations. So we can start and stop a recording. We can see how much memory is left. We can come down here and click the RMS tab and look at the RMS data. We can come and click the demand tab and look at the demand data, and the events tab and look at the different events that may have happened. We can also transfer the data remotely or have it automatically transferred periodically, so you don't have to go back to the unit to retrieve your data. So this is what a good power quality analyzer package should include. Of course, your power quality analyzer, your CTs. I would suggest getting a analyzer that uses smart CTs so that it'll tell you if you connected improperly before you leave. That way you ensure that you get the correct data the first time. For these CTs here are 4-range CTs as well, so you don't have to carry a bunch of CTs. I would suggest that. Also, having some small plunger clips so that you can get to the harder to reach places to hook your voltage leads up to. And also a 32 gig SD card so that you can have long recordings for over a year if necessary. So Megger's NPQ1000 is not just a logger, it's also an onboard analyzer. So you can look at your motors in real time and make sure that they are running efficiently as possible. Other useful tools I want to mention that Megger has to offer for testing motors are the DLRO, or the Digital Low Resistance Ohm Meter, for doing bar-to-bar tests on DC motor, and the MIT series insulation resistance testers to check the insulation resistance from phase to phase and from phases to earth or phases to frame. With Megger's acquisition of Baker, we also now offer these units that do the famous Baker surge test. Transcat does carry these now as well, so you can feel free to request a quote if necessary. And with that, I want to thank you for your time, for joining me today, and I will open it up for questions and answers.
All right, so if anybody has any questions, you can just type into that box, the question box down on the right-hand side, and then we'll get to them in the order they come into. Okay, here's our first question, Jason. What causes high-frequency harmonics?
Okay, well, things like VFDs use high-speed switching insulated gate bipolar transistors, or IGBTs, which produce high-frequency harmonics. So do high-speed inverters like the ones used in solar. It's the high-speed switching that's creating these higher frequency harmonics.
Okay. Let's see, our next question here is, what causes high or low voltages which lead to overheating?
Okay. Things like switching off large loads, such as motors, like I said earlier, cat bank switching, Even wrong tap settings on the transformer can cause an overvoltage. When it comes to undervoltages, things like switching on big loads or overloaded circuits will cause an undervoltage.
Okay. Again, anybody else with questions, just type them in the question box on the lower right of your screen, and we'll get to them in the order they come in. All right, here's one. Is there software required to connect MPQ to a network for remote analysis?
Yeah. So a good power quality analyzer is going to come with the software to allow you to do that. Absolutely. Again, I would suggest going with a unit that gives you the software for free. Like the MPQ 1000, Megger's MPQ 1000, it does come free and it's unlicensed, and it does allow you to do that.
Okay. Next question. How do I determine the configuration of my motor?
Okay. Well, first off, I would check the nameplate, of course. Then also look to see how many wires are coming from the motor. You may have 3, 6, 9, or 12 wires. So depending on the number of wires, you may be able to actually configure your motor in a delta or Y, and at multiple voltages. But I would start at the nameplate. The nameplate should tell you what you need to know.
Okay. What can cause the shaft of a motor to break in operation?
Well, vibration, misalignment. Off the top of my head, it would be cool to see that happen, but vibration can lead to that, as well as misalignment, or even just a manufacturing defect.
Okay. What would normally cause a motor to burn a winding after a few weeks of service? All readings are open and ground, but one winding reads 97 ohms, where the other two read 2.3 ohms. Motor runs 2 minutes and off for 7. Scope meter shows, there's a little bit more here. Scope meter shows 100 volts or more, even every 45 minutes. And it shows up at startup. So he says, I think it might be coming from spikes at startup.
Yeah, that's what it sounds like. It sounds like it's definitely spikes. It could be from startup. It could be something that's transient related. I'm not sure where he or she lives at. But lightning causes a lot of transients, so depending on the area that you're in. But it does sound like it sounds like it's something to do with the startup. You may have it too much of a load on the motor at that startup.
Okay, he just posted some additional info. Motor is a 9-wire wired 460 in a delta with an ungrounded delta power feed. Volts are 488, 488, and 489 volts at a power plant.
Okay. Yeah. I would still say the same thing. That's what it sounds like, based on the information that he's given us.
Okay. He also says the current is normal.
The current's normal?
Yep.
Okay. I'd be happy to take his call. If he'd like to give me a call too, I can maybe help him out. But yeah, I would say it's something that's spiking it. I mean, it's something that's degrading the insulation from the winding.
All right, I'll get you his contact
But
info.
it could just be heat.
Okay. Here's another question. I've been told by oh, go ahead.
Hold on, one sec, I'm sorry. They say for this 10 centigrade rise in temperature reduces the life of the motor windings by 50%. So just 10 degrees C rise can ruin those windings.
Okay, I got a phone number you can reach him at if you want to call him back after the webinar.
Yeah, I'll do that.
Okay. Next question. I have been told by our local motor shop that overgreasing can be worse than undergreasing bearings. What are your thoughts?
I agree. Yeah. You don't want to do too much because it's just creating because then you kind of can create the pitting and fluting if you overdo it there.
Okay. Our next question is, what causes current to pass through the bearings?
That's a good one. So when the motor shaft is turning, right? Try to picture this. So when the motor shaft is turning, the bearing grease is acting as an insulator. So it's insulating the bearings from the bearing race, which that is now acting as a capacitor. So the stator and the rotor are generate a charge through capacitive coupling, which is electrostatically induced into the motor shaft. And so once this current passes through the motor shaft to the bearings, it creates the discharge between the bearing and the race. And that's actually what can cause the pitting and the fluting effect that I was talking about earlier.
Okay. The next question is, will the Q&A be included with the slides? And I'll answer this one. This entire presentation is being recorded, so you're going to get a copy of this recording with all the questions. You're also going to get a separate copy of just the PowerPoint slides. So it'll actually be in the recorded session, not in the slides. All right, I'll leave it open for a few more seconds to see if any more questions come in.
Okay.
It looks like we've got to everything that people are going to send in today. So I guess that concludes our time for today. If you do have further questions or you'd like to find out more about Transcat's product and service offerings, please contact us at 800-5001. We're on the web at www.transcat.com, or you can email our marketing director directly at nvanwert@transcat.com. Thank you for joining us today, and we hope you got something out of today's presentation and that you continue to join us for future Transcat e-learning webinars.
Thanks again, guys. Hey, Mike.